Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to continue talking about acid-base properties of ions and salts. But in this particular video we're going to talk about how to determine the pH of a solution that contains an ion that acts as a weak base. So in my previous video we talked about anions and how they can act as either bases or neutral substances. And so here we're going to talk about how do you calculate the pH of that weak base or that anion. Okay, so let's get into this. So again, we're going to determine how do you find the pH of a solution that has the conjugate acid or the conjugate base of a weak acid, or has an anion that acts as a weak base. So um, basically, it's like finding the pH of a weak base, right? So we saw before that if you have a weak base, you would then figure out what the ionization or the base ionization constant is of that. And then you would set up your KB expression, do your ice table to figure out how much OH is produced, plug that into your KB expression in the terms of X, right? So you're going to do your ice table. And in your ice table, you would figure out the equilibrium concentrations in terms of X, plug that into your KB expression, right? So your KB expression. And then you would find X either by using the X's small approximation, or if that doesn't work, if that doesn't uh, uh, obey the 5% rule, then you'd have to use either the quadratic formula or you'd have to do the method of successive approximations. So once you get the value of X, then you would that would be the OH minus concentration, and then you would figure out the pH from there. Either plugging the OH minus into your negative log, take the negative log of the OH minus, get the POH, and then subtract that from 14 because the POH plus the pH is equal to 14. Or you can use the KW is equal to the concentration of OH minus multiplied by the concentration of H plus, and then you can solve for H plus that way, and then take the negative log of the H plus. Okay, so basically we're going to use the method of a weak base, since that's what the anion is. So if the anion is the conjugate base of a weak acid, then this is going to be a weak base. So you need to first find the Kb, right? So you're going to find the Kb from the Ka of the acid from which the weak base or the anion came from. So here you can see that here's our weak acid. It's going to react with water. It's going to form the hydronium ion plus your weak your anion here, and this is the anion that is acting as a weak base. So this anion that acts as a weak base, you put that in water, that's going to take a hydrogen from water, it's going to ionize the water, give you the weak acid back, and then you have OH minus here. So since this is acting as a base, we need a Kb value. So we can write the Ka and Kb values like we normally do, right? So the Ka value for your generic acid is going to be the concentration of hydronium ion multiplied by the concentration of your anion, and then divided by the concentration of your acid. So the Kb value for your anion is going to be written the same way. So since your anion here is acting as a base, the Kb for this anion is going to be the concentration of your Ha multiplied by the concentration of your hydroxide ion divided by the concentration of your anion here. So this is the Kb expression. But how do we find the Kb for this anion? So we're readily given the Ka value for your acid, your weak acid. So you can look that up in a table, or it's given to you in the problem, but you can readily find this. If we know this, then we can find the Kb. How do we do that? Well, this expression here. if we take the Ka and the Kb values and we multiply them, right? So we take these values and their expressions and we multiply them, look what happens. So if we multiply the Ka expression by the Kb expression, we notice that we have A minus concentration here, A minus concentration there. So that's going to cancel out, right? And we have the HA concentration here and the HA concentration there, so that's going to cancel out. And what are we left with? We're left with the concentration of hydronium multiplied by the concentration of OH. So let's write that. So the concentration of H3O plus multiplied by the concentration of OH minus. And what is that? We've seen that before. The H plus concentration multiplied by the OH minus concentration, that is equal to Kw, which is again equal to 1.0 times 10 to the negative 14. Okay, so basically, what does that tell us? That tells us, if we shorten this, that the Ka multiplied by the Kb is equal to Kw, which again is equal to 1.0 times 10 to the negative 14. So now we have an equation that we can use to find the Kb's of your conjugate bases, of the anion of a conjugate acid. So here is an example. So I have acetic acid. I'm given that the Ka of the acetic acid is 1.8 times 10 to the negative 5. Well, notice that here the HC2 H3O2 acid, right? That's going to react with water, and that's going to form, it's a weak acid, acetic acid is weak acid, that's going to form C2H3O2 minus plus H3O plus aqueous. Okay, so here we have the anion. This is the anion of a weak acid, so this is a weak base. So if I wanted to find out, like say for example, the Kb of this weak base, then what I can do, so the base would be here. So the reaction with the base would be C2H3O2 minus aqueous plus water, liquid water, and that's going to be in equilibrium with, it's going to take a hydrogen from the water, so it's going to reform the acid HC2H3O2 aqueous plus OH minus aqueous. So here is the reaction of the anion with water. So what would be the Kb of this expression? I'm giving the Ka of this reaction here. So this is the Ka that I've got. So that's equal to 1.8 times 10 to the negative 5. Well, what about this reaction with the anion? What's the Kb for that? So to find that, I use this expression here. So I know that Ka times Kb is equal to Kw, so I can use that. So here, I know that Ka is equal to 1.8 times 10 to the negative 5 multiplied by the Kb, and that's going to be equal to the Kw, which is 1.0 times 10 to the negative 14. So then all I need to do is divide both sides by 1.8 times 10 to the negative 5, and I end up with my Kb. So in this case, Kb would be equal to whatever that number is. So if we calculate that really quickly, there it is. So we have 1.0 negative 14 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 equals, and I get 5.55. So then I end up with 5.56 times 10 to the negative, I believe it was 10, negative 10. And so that is the Kb of the conjugate base, the anion here. So the acetic acetate ion here, now we know the Kb for this acetate ion. So now I can use the Kb value to figure out the OH minus concentration for a given concentration of this acid using my ice table. So remember, so now that we have the Kb, if I'm given in a problem, I'm given a certain concentration of my acetate ion, I can use my ice table to figure out like how much, get the expressions of the equilibrium problems in terms of x, the equilibrium concentrations in terms of x. And once I have that, I can plug that into my Kb expression for the acetate ion, solve x, find x, and then x would be the OH minus concentration. And then from there, I can calculate the pH, as I said before. So I hope this is helpful. I hope you learned something from this. I hope this clarified some things for you. In other videos, I'll be doing example problems, so you check those videos out, and so you'll see how I apply this to actual problems. So thanks for joining me. If you like this video, please hit that like button right there. Subscribe to my channel. Hit that notification bell so that you can be notified by other videos I put out. Put a comment in the comment section. Let me know what you think. If you have any questions or need clarification on anything, please ask. Thanks for joining me. Have a great day.